So here's the thrown chalk problem that we did in class. I'm going to do it again, and this time I'm going to do it by making positive up. People seem to be more comfortable with that. So we'll do that first, and then maybe you can go back and think about it with positive direction down. So remember, it was just the case we throw chalk down at 2 meters per second from the origin at time equals 0. So the experiment is like this, a little piece of chalk, and we just want to know how far does it get at t equals 0.25 seconds. So the drawing is the same. We have the little piece of chalk here, and we give it a VI, and we threw it at 2 meters per second. That means when we released it, and it was no longer under the influence of our hand, it was going 2 meters per second. And that's when the problem starts, when it is released from our hand. So an initial VI, 2 meters per second, we said it is from the origin, so even if you define up as positive, we got to put the origin there, plus x. So the question is, where is it at t equals 0.25? So still, it is a plug and chug problem. You just put in the values for x final equals x initial plus v initial t plus 1/2 a t squared. So let's put in some values. X initial is 0 because it's at the origin. V initial, we said, is negative 2 meters per second because it's down, and we defined up as positive, plus negative 2 meters per second, and the time we're trying to figure out for the position is 0.25 seconds. So just like I told you on day 1, we might not write the final position as a function of time. You have to know from context, this is the final position as a function of time. And then plus 1/2. And now the acceleration. So when something is free, moving freely through the air, nothing touching it, the acceleration is always 9.8 meters per second down. Down might be positive, down might be negative, but it's down. So we defined up as positive, therefore down is negative. So we put negative 9.8 meters per second squared. And then the time we're looking at is 0.25 seconds squared. Someone asked if we have to write the unit in every time, and you don't. It's a good idea, though, to keep up with the units as you go. What this is going to result in is really the same two numbers we got before, but now they're both negative. So let's see, I've already done the numbers ahead of time. Actually, I don't have the intermediate numbers, but when you add this negative number and this negative number, you get negative 0.81 meters. And you say, now why is the answer negative? Because it's going to end up somewhere below the origin. It's going to end up down here. We defined up as positive. That's why when I did it in class, I thought, oh, we'll make down positive. Everything will be positive. Everybody will be happy. Okay, not quite. Okay, so in this, doing it this way, the answer is negative 0.81 meters. Where is it? Yeah, it's there. Okay. So in a problem where you have to enter the solution on line, we would have to tell you which way is positive. And usually we do that, or we assume it's obvious. Okay. Then the next part was, what if we threw the chalk up instead of down? So that's kind of like A. And B, what if VI equals, in this case, we're saying it's positive 2 meters per second. Okay. Here it was negative, and I didn't write a negative sign here, but I pointed an arrow down, because this is just the drawing. When I plugged it in, I put negative. So now it is plus. Well, you just plug in the same equation. That x final equals x initial, which is 0, plus v initial t. Oh, we can go ahead and be plugging in. Plus positive 2 meters per second, 0.25, plus 1/2, but it's still, let's see, we defined, we threw it up. It's still negative 9.8 meters per second squared, minus 9.8 meters per second squared. Even though you throw it up, it doesn't matter. It doesn't matter which way you throw something or how you throw it. As long as it's free of your hand, the acceleration due to gravity is down. So it's 9.8 down. We defined up as positive. It's still negative 9.8. If it's moving up at negative 9.8 acceleration, that means it's slowing down. If it's moving down with negative 9.8, it means it's speeding up. But during the whole path, it's negative 9.8 meters per second squared, if you define positive as up. All right? So when you solve it this way, you'll get a different answer. You can see you have a positive term and a negative term, and in the end, you get, in this case, plus 0.194 meters. Let's see what you would get there. Yeah, that was what was, yeah. And then my final question, sort of for funsies, is, okay, it went up and down. Is it at 0.194 at the beginning, on the way up, or is it at 0.194 when it came back down? And for that, we would go to part C and say, well, all we need to know is what is the sign of the velocity at t equals 0.25. Is it positive, moving up, or is it negative, moving down? For that, you go to the other kinematics equation, v final equals v initial plus at. Okay. In this case, v initial is 2 meters per second. We got to say if we're throwing it up or down, we're throwing it up. That's the point of this one, is you throw it up, it hits this position twice. So if it's up is positive, that is 2 meters per second. Plus A, no, A is negative 9.8, because we have defined up as positive and down as negative, and then times 0.25. And then you get the final velocity is, let's see, that's about negative 2.5 and 2. It's about negative 0.45 in this case. And since it came out negative, you know that the velocity is down. So that means it went up, and we caught it coming down at 0.25 seconds for the case that we throw it up. Someone asked about drawing the graphs. It's a good idea to think about the kinematics graph for any problem that you do. And let's see, so here, let's just plot it like this. Here's x, and here's time. Let's think. Let's do it for part A first. Threw it down. It started at the origin. You know it started at the origin. You threw it. So you gave it an initial velocity down. So it's going to have a slope negative at the very beginning, because you threw it down. Down. And then the acceleration is going to make it curve down, because the downward velocity is increasing. Here it is getting a bigger and bigger magnitude. So it basically looks like that. So curve because of gravity, and then going and initially having a slope down. We could plot the velocity. Again, this is all for condition A, where we threw it down. The velocity curve, well, let's see. We initially had a negative velocity because we threw it down. So we'd start here, and then we know a uniform acceleration due to gravity will cause this to be a line. Right? The slope of this has to be negative 9.8. It starts there and it goes down. So that'd be the velocity curve. Let's do it for B. Let me just make myself a little room here. And for B, let's see where we threw it up. There's x, and there's time. Start at the origin. We threw it up, and it's just a free, it's a parabolic trajectory, right? It has an initial velocity up, but that slope is being reduced by the downward acceleration. So it's going to go like that. And this is when it gets back to the level we threw it from. If you want to let it hit the floor, then it would keep going. I think somebody asked, would it cross the time axis? All crossing the time axis means in this drawing is that it gets back to the origin. So if I threw it here and threw it up, yeah, it gets back to the origin when it passes my hand. Here, it never gets back to the origin. It goes to the ground. So maybe in class it wasn't clear which case I was drawing. This is B. So hopefully that helps. Hopefully positive being up helps you see what's going on in the problem.